Very good evening from Physics for Students. My name is Shaunak, and welcome to this very special evening today. We are trying to explain Dirac equation. Is it now clear? Can anybody just tell me better? Okay, fine. Okay, so I will just put it over here. Yeah, okay, great. Thank you. So I hope that everybody is safe out there in Calcutta, because there are some unfortunate events which happened and the mob is very angry. So just wanted to make sure, because we are a family, and hope everybody is okay. Yeah, thank you. Thank you, Edie. Okay, so who was Paul Dirac? We know that very recently audio is good, but a high volume would be better. Okay, high volume. I will try to put it over here and listen. Praetor Akin. Okay, so we know we just celebrated his birthday on the 8th of August. He was an English mathematician and a theoretical physicist, right? And he is known as the purest soul in mathematics. I mean, it's the purest soul in science. So he was considered to be one of the founders of quantum mechanics. He laid both for quantum electrodynamics and quantum field theory. He was the Lucasian professor of mathematics, most importantly, at the University of Cambridge, which was held by Isaac Newton and later by Stephen Hawking. And in 1993, he won the Nobel Prize in Physics along with Erwin Schrodinger. Okay, I will just like to show you one book which I'm reading recently. Just a second, I will just call my daughter to give me that book. If you can just help me with that. I will show you. That is a wonderful book to go through. This is actually the address of 15 Monk Road, Bishopston, Bristol. And this is a plaque which is written after his death. And this reads, actually, this is the house, and it actually reads. Yeah, thank you very much. So I'd just like to show you this book, which I'm currently going through, almost done with the pages. Just few, I will finish it up. This is an absolutely great book. Now, this book, I just wanted to tell you that the good part of this book is that for people who are starters, it doesn't contain any difficult equations, number one. Second is that it gives not only a complete account of Erwin Schrödinger's life, but it also goes through the First World War, the Second World War, and even I was surprised to find that Erwin Schrödinger has to leave his Nobel Prize at Berlin after the Nazi occupation, and with one Reich marks, he and his wife Annie, they have to leave Berlin because of the Nazi occupation, go to Ireland, Dublin, where he center. It's so something like that. So this is a really wonderful book which contains a lot of beautiful images and writings, not very expensive also. You can see this. So this is a very good book to read. I am going through that, and I will finish it off by tomorrow, and I will go for the next book of Paul Dirac. Okay, so I will get back to that. Otherwise, it would be late because we have to cover up a lot of important topics. So this was his father, Charles Dirac. Felix, his brother, somehow committed suicide, which is a very sad thing because his father was so strict that he wanted to pursue a discipline, but Felix wanted to pursue something else and he committed suicide. This is Paul Dirac, his mother Florence, and the name Florence was given by his, by his father's mother, when they were actually on a trip, when they met actually Florence Nightingale, and Florence Nightingale actually just told that, why don't you name it? So Father Charles was a very strict person, and he only asked to speak in French, and after a lot of when his father died, there's a statement where Dirac told that I'm very happy now that I'm alone, because he was a very silent person, and Charles was constantly pressing to speak only in French, and he was a dominating personality. So the rest of the thing I have covered in my earlier videos, I won't go. I will directly go to the mathematics part, and we start with this. Now, as we know, I will just put off the slide for a few seconds. As we know that Dirac equation till now is one of the most successful, I would say, equation which actually plugged in quantum mechanics and special theory of relativity. To be very honest, as you all know that I'm personally a specialist in general relativity, but till now, no other theories have plugged together. Tomorrow we have Professor Joseph Conlon, coming from Oxford University, in a special podcast tomorrow, where he will be speaking on string theory. But this is one of the most successful equation, and it has been proved through experiments, etc., that this is absolutely okay with special relativity. So first thing that we need to understand over here is that why do we need to plug in special relativity in Dirac equation? So till now, what we have seen, that all the motion of bodies, which is more or less than the speed of light, or we can say for example, this should be on the other side. I think I made a mistake. Anyway, anything which is moving less than the speed of the light, I have mentioned, I think it is greater. It should be less than. Yeah, less than the speed of light, etc., are all well guided by Newtonian mechanics. Anything which is equal to, or it should not be more than, but more or less equal to or moving near to the speed of light, they are all well guided by special relativity. And the quantum world, which is very small, I am taking Schrodinger equation and the Heisenberg's uncertainty principle, because we are talking of the time when Paul Dirac is not into the scene, was not there. So these three things were well established. Quantum physics guided by Schrodinger equation, Newtonian mechanics guiding all those which are moving less than the speed of light, and special relativity, which are approximately close to the speed of light. So the need was that, can we unify those things? Can we unify to get a better theory? So motion of bodies which is traveling close to the speed of light and the quantum world, there was a need that we get a unified and a relativistic theory of physics. We cannot put in relativity separately. We cannot put in quantum physics separately. Quantum physics was well established by that time, 1920, 25. And we are, the scientists were trying to achieve a relativistic quantum physics. So there were earlier attempts for a relativistic quantum mechanics. Schrodinger equation was classical, and Klein Gordon equation, as we will see, this is very important, that was an attempt to unify quantum mechanics. Partly it was successful also, but there was something but dot dot dot. So we will first see that there is a need for a relativistic quantum physics. Now, when we talk about relativistic quantum physics, first what we need to go is that we need to understand what is a Schrodinger equation. We all know what is a Schrodinger equation, but I want to give you a different aspect of Schrodinger equation by telling that what actually it is. Okay, I have skipped the derivation, but what I am trying to make over here is a point that if we have a mass, say m, which is this yellow ball, and if it is moving at a constant velocity v, okay, and it gets a kinetic energy which is half mv square. It's a school level physics, and we know that momentum is given by p equals to mv, right? So if we just swap the values, we get v equals to p by m, right? And when we substitute this value, we get k equals to 1/2 m followed by p by m square, which we simplify, and we get k equals to p square by 2m, right? Now this is something which is quite similar. I mean to say, what is that similarity? I will just show you. Now you see, this is the Schrodinger equation. This is the one of the form of Schrodinger equation. They have many forms, the time dependent, time independent. I've kept a general form, right? Now here you can see that the one which is in the box, this is actually the kinetic energy, right? So first what we get is that Schrodinger equation tells that the particle which is moving not at the close to the speed of light, mind it, because it is a non-relativistic, which is moving at a decent speed, we get p square by 2m. This is the kinetic energy. Now suppose that m, that yellow ball, we give a kind of a potential energy. You know, potential energy again can be various types, right? Equals to gravitational potential energy, Coulomb's static law, electrostatic, a lot of things. So what I have done is that I have just taken a general potential energy, V of x, right? It represents the potential energy that influences the quantum particle's behavior at a position. It's a general. Now you note that I have put a hat sign over p and a hat sign over v. I will going to explain what are those. Those are quantum operators. So let us understand that we have got a kinetic energy p square by 2m, which very classically comes from Newton's law, and we can put it over here. And we get a v, which is the potential energy, and here we substitute it over here. So what is the Schrodinger equation telling? It is telling simple: kinetic energy plus potential energy equals to total energy. It is nothing great. To be very honest, if you talk in a very classical manner, then it is just this. It is the classical kinetic energy plus the classical potential energy, which is equal to the total energy. But we have something which is a hat, etc., which I'm going to explain next. Now you see that this is, I mean to say, this can be elaborated a lot, but this p hat is basically what is called the kinetic energy operator, and the v hat is basically the potential energy, or the energy operator that we are talking. Now remember one thing, that in quantum mechanics all these operators do act on a wave function, right? And the wave function, actually I can use this word, encapsulate the data. So if I get a kind of an electron which is moving from this part to this part, where it is going, what is the probability amplitude, what is the chance of finding that electron over here or here, all these are dictated by the wave function. So as I have written, that the wave function gives the information about the different probabilities. I should say it is actually the square of the probabilities as per Bond's rule, but I have avoided that. So what we get from here is that these momentum operators, or the potential energy or the kinetic energy, all these operators actually act upon the wave function. And the wave function in return provides a very complete description of where the particle it is, where it will go, all those things. Okay. Now, one thing that you see in the Schrodinger equation, that the time and the space are treated differently. Now, remember one thing, that in special theory of relativity, when we generalized from Newton's laws of motion, time and space are now a space-time continuum, either in a Minkowski diagram or whatsoever. But what you see over here is that time and space are differently treated. Why? Because we get a first derivative in time, because Schrodinger takes time as a universal time component, and we get x squared. That means the second derivative in terms of space. So the second order space derivative, actually it corresponds to the kinetic energy, which is governed by the Hamiltonian. But what we can understand from the Schrodinger equation is that time and space are treated differently. And this gives a hint that it is not relativistic. Absolutely clear on that. Because we will see that how time and space is united by a single derivative, because time and space is actually treated in two different ways, which is actually not right. We have got a single derivative in time and we have got a second derivative in space. So from here, what we can tell actually is this one, that it does not maintain the same form of Lorentz transformation. The separate treatment of time and space derivative breaks the symmetry required by special relativity. So what is the objective? In order to get, the objective is that we should get an equation which is Lorentz invariant. That means it should not change the form under Lorentz transformation. So you see the second line, if you transform time and space coordinates according to Lorentz transformation, the Schrodinger equation structure would change, and this is not what we want. So again, it proves that this is actually a problem in terms of getting a relativistic equation. The first problem is that the time and space is differently used, and second is that it does not maintain the Lorentz boost, the Lorentz transformation. Now, one thing I have not mentioned over here is that spin of an electron, the way it moves, that also is not encountered in Schrodinger equation. Now you might say that why spin was not being encountered during that time. Now the reason is that spin probably, when we are talking of Schrodinger's time, was not known clearly. The concept of spin came from what we call the Stern-Gerlach experiment. Let me see the year of Stern-Gerlach experiment. Do you know anybody? You can put it in the comment box. The Stern-Gerlach experiment was done in which year? Let me check the Stern-Gerlach experiment. I think it is done around, 1922. So before this Stern-Gerlach experiment, there was no evidence that we can find out the spin. So the spin part is not being considered. The relativistic part is also being considered due to those mathematical reasons. Now, the next attempt the very first attempt, I should say, which was done in order to unite relativity and quantum mechanics, were done by these two gentlemen, the Klein and Gordon. We will come to that part actually. Now, I cannot find any photograph of Walter Gordon. Oscar Klein I have been able to find out, but Walter Gordon, I searched in internet, contacted few people. I don't know if you have any photograph of Walter Gordon. Do let me know. So this Klein Gordon equation, the first thing is that is an attempt to unite special theory of relativity. And we all know that special theory of relativity, the cornerstone of the equation is Einstein's special theory of relativity, E equals to mc squared. 1926, I think you are right, Jagat. It should be around 1926. Thank you for this. Okay, can anybody put up a comment that is it all going okay? I mean, are you enjoying and learning things? Because you people remain so silent, I don't understand. Is it all okay? You're going okay? Things are fine? You're learning things? Do let me know in a yes or no. Okay. So, okay, it's personal says yes. Thank you very much. This gives a kind of a motivation, because as I cannot hear anybody, I feel so bad. Yeah, Ankur Haldar. Thank you very much. Okay. So the E equals to mc squared. But remember, this is not a proper equation because it deals with objects which are not moving. So what about an equation where the objects are moving? We know this is the equation. Okay. E squared equal to mc squared plus pc squared, where the pc squared, the blue part, is, thank you, KVMK, is the momentum part. Now you see, we know that photons have momentum. Now here is a kind of a fight. Now you might fight with me. You might say that, sir, photons also have mass. Some people will say that photons do not have mass. I don't want to go into that argument, but what we know is that photons do have a momentum, whether it is a massless particle or not. So if I take P equals to mv, the classical Newtonian momentum formula, this is applicable where m is not equal to 0. That means m has a mass, whatever, very small mass, let it be. But if I take m equals to 0, that means photons, for example, I assume, I don't know, I save my questions for the end. Fine, no problem. You can ask me questions at the end. Thank you. So m equals to 0, I mean to say, if I take the mass of a photon to be 0, then that part goes 0, m becomes 0. So we can find out E square equal to P square C square, and then we get P equals to E by C, right? This is something that we get. Now, what is the reason P equals to E by C? Okay, before that, I will like to show you. This was Oscar Benjamin Klein and Walter Gordon who actually made the experiment over there. So we were talking of the momentum, about the P equal to mv, where mass is not equal to 0, and this is mass equals to 0. Now, this is something I don't want you to go through the derivation or a different thing. What I'm trying to make you understand is that through a mathematical manipulation, don't worry, I will show you the Klein-Gordon equation derivation later in a video, because right now I need a pen and a paper to do that. So it is not here over here. But this is very simple. There are various ways of getting into Klein-Gordon equation. So this one, and this one, all these three are different forms of Klein-Gordon equation. The first one, take the Laplacian. If I replace the Laplacian and the second order derivative with the D'Alembert operator, then it becomes a kind of a box. So what ultimately Klein-Gordon equation tells is that those without any remember, this also does not contain the spin. As soon as the spin comes in, our life is going to be hell. I can tell you, I will tell you why. So those without any internal spin, like for example, hypothetical particles, Klein-Gordon actually framed it with spin equals to 0, move and behave in this way. So when you take both quantum mechanics and Einstein's special theory of relativity into account, this type of equation. So what this equation tells? The equation tells that if you take a particle which is moving at a closed speed of light or equal to the speed of light, and it is put up in a certain setup where it goes, where it will come into all sorts of combinations of predicting or the movement or the kinematics of a particle. That is basically taken. But remember, again, it does not take into account spin. Now, this is a absolutely great and a wonderful attempt. It was very successful in one time, and it actually got hold of what is called the relativistic wave equation. So now you see what it actually tells in a simple word. You can read out the red part. It tells us how the wave-like nature of these particles changes over time and space. Schrodinger equation also does that. It takes a system and it shows how it evolves. All right. Unlike the more familiar Schrodinger equation works for slower speed, everyday speed. This is for higher speed. All right. And that are moving close to the speed of light ensures that the rules of relativity are being established. Now, there is one striking feature which I have not shown because I was doing the derivation on my diary. I mean to say on a pen and a paper, which I came into this. Okay. Don't worry if you don't understand. This is a kind of a derivation of the Klein Gordon equation. The most important you see now, all these derivatives are second order. If I go back to my slide once, just hold on for a second. If you remember this, you see that the time was taken in a first derivative and space was taken in a second derivative. But the Klein Gordon equation is so beautiful that it actually takes everything in the second order derivative, t for time, x, y, and z, and it does not change under Lorentz transformation. That means it is Lorentz invariant, and that is wonderful because we were actually targeting something which would be Lorentz invariant, which would be relativistic, which will follow the special theory of relativity, which will follow the wave mechanics, and it will also follow spin, which somehow is not being taken care in the Klein Gordon equation. Now, the Klein Gordon equation, being the first to take care of the relativistic part, had certain problems. I'm to say mathematical problems, which resulted into certain physical problems. Now, you see, the first thing which I wanted to note, don't go immediately to the lower end. First, concentrate on the density, the square of the amplitude. Now, in Schrodinger equation, if we square the wave function, we get the probability density. That means how much probability is for the electron to be in a certain area, this or that or whatever, right? But here you see the psi which takes place, it actually shows our negative probabilities. And negative probability is something which has no sense. What do you mean by negative probability? It doesn't have any sense in the physical world. So now you see that on the left hand side, this is a Klein Gordon equation. This psi has no probabilistic interpretation. In some way, we call it as a charge density, but that is an interpretation. But what it says is that it allows, for the second derivative of time, it allows densities to be negative. If I consider that there is no probability, if I consider that to be a density, but that density also comes out to be negative, which is physically not the right way to do. Okay, that is the first problem. So also the second problem was that Klein Gordon describes taking spin 0, which are mesons, which are, I would say, hypothetical particles. And it does not describe with spin of electrons or any fermions with spin half or spin 1 or nothing. So the first problem was that it was covering what is called this one, the negative probability part, you want it to be negative, and it is not considering the spin of that part. So that was basically the problem. Now, if I show you the equation side by side, you can see that the Klein Gordon equation with a phi given on that, this is again a derivation. Don't go that why it has come. I will tell you later, but you can just believe on my words that this phi on the Klein Gordon equation is a relativistic equation, but it is for a scalar field. It gives for a scalar field. But now we will see the Dirac equation, which is basically what is called a spinor field. And this spinor, I'm very sorry to tell you, it's a very advanced concept in physics. And it would require at least 1 hour to make people understand about spinor. And I have to make a video, or I can make a live session also to make you understand about spinors. And spinors can be actually described using what is called polarization of light, the vertical polarization, the horizontal polarization. So spinors are not that they need something for relativity only. Spinors are something like Jones vector, which can be used in classical electromagnetism also in order to describe things. But anyway, what I'm trying to tell is that this is a scalar field, and what we will see, Dirac equation, is what is called a spinor field. So as soon as we say what is a spin and a spinor, in this part of the video, before going into the relativistic Dirac equation, I would like to explain you in simple words what is a spin and what is a spinor. I hope things are going great. Okay. Now, if you take the standard model of particle physics, you will see that the bosons, which are basically called the force carriers, those which carries the force, they either have a spin 1 or a spin 0. I mean, so the gluon, the photon, the WZ bosons, and even the Higgs boson. So if I get a spin 1, I don't have a board over here, I better to use on my classes. So if I got a spin 0 or spin 1, whatever the orientation it happens, that can actually be explained through what is called a vector, right? If it is a spin 1, it is a spin 0, it can be explained by scalars. Now, the problem is that with the fermions, fermions means you, me, the table, the chair, the universe, all that matter particles, whatever constitutes of the matter. So the electron, the proton, the neutron, and everything, they have got a spin half. Now, this spin 1.5, it doesn't actually mean that it will just rotate half. No. As a matter of fact, you need to also understand that when we talk of the spin of an electron, it doesn't actually spin like a spinning top or a planet orbiting around the sun. It is not like that. It is something which is very internal, which is called the angular momentum. We will explain spin as much as I can in today's live, but spin would again take a different kind of a session, because spin is something very very intrinsic. It actually doesn't carry anything related to what we perceive as spin. So the fermions and the matter particles, just a second. Matter particles, they are actually having a spin half, and this is being explained as a spinor. Okay. Ankur Haldar says it is the same as vector 0 representation of 1/1 and representation. Yeah, almost. Representation and spinor 0, it won't be actually denoted by 0, half, but it depends upon whether you're using a Weil spinor or a Dirac spinor. But yes, you are absolutely right. It is more or less that kind of an expression. Ankur, you're absolutely right. You're right on the path. Okay. Now concentrate on this one. Now you see that in case of a vector, if I make a 360 degrees turn, okay, imagine the vector is going down, 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 and it is coming back. So at 90 degrees, a 180 degree, and then again a 90 degree and a 360 degree. Okay. So if I take any vector, I move here, I move here, I move here, and I come back. So this shows that a vector retains its position with a 360 degrees turn, which is not happening in case of a spinor. The first diagram on the right hand side shows that if the spinor is a mathematical object, right? If it takes a 180 degree turn or a 360 degrees turn, then it actually comes back to a position where the sign is a negative sign. So if I consider that the vector is positive after 360 degrees, it will come back to positive sign. But in case of a spinor, which is coming back to minus, it is coming back to minus. That means the sign is not retained. So it needs what is called a 720 degree rotation in order to come back to its original position. And remember that electrons also actually make a spin half. Now, you might ask me, what is spin half? Actually, spin half means either the electron is spinning up or spinning down. Spinning up means it is a plus. I have to make another session with that. As I told you, electron spin is a very deep subject. Either it is spinning up or it is spinning down. So spin up and spin down, either +1 or -1. It's a quantized quantity, right? So what do we see from here? That if a vector makes a 360 degrees turn, it comes back to its original position. Spinors require a 720 degree turn in order to come back to its position. And if it makes a 360 degrees turn, what is going to happen? It is going to take a different sign, and our mathematics is going to be wrong. So here you can read that electron spin is basically a quantum property which is very intrinsic. We will now see what do I mean by intrinsic in the Stern-Gerlach experiment. This is not something we can visualize directly, right? But it is a key feature and gives what is called a magnetic moment of an electron. Now, unlike regular vectors, spinors transform different. Now, this is again a big question. How do spinors transform under Lorentz transformation? It will take a little bit more time to explain, which is out of the scope. I will do it one by one in the videos. So just to get a hang over it, understand that if you rotate vector by 360 degrees, it will come back to the original space. But if you rotate a spinor by 360 degrees, it will change the sign, and it is a full rotation of 720 degrees is required in order to get it done. Okay, so this is actually the concept why we need a spinor in order to describe the spin of an electron. Okay, we come to the Stern-Gerlach experiment. Now you see that what happened is that there are two magnetic, it's a very scientific and a different experiment, but it has got two poles, magnetic poles, north and south, and there is a electron, a photon which is being passed through that, any particle. And what we see is that due to the orientation pattern, it is either moving in a spin up position or it is going down in the spin down position. Right? So that means it is actually taking what is called a quantized spatial orientation. So here you see that the spatial orientation of angular momentum is quantized. Thus, an atomic scale system was shown to have intrinsically quantum properties. Now, actually, the Stern-Gerlach experiment used what is called silver atoms. I will come to that, why they are using silver atoms. But what is clear from that, due to the orientation pattern, it will go either in a spin up position or in a spin down position. Absolutely. You are very true. It's absolutely correct. Or I can say inhomogeneous or non-homogeneous magnetic field. Its personnel has got right up to the point. Thank you very much. Now, there is another thing which I have not mentioned, but it is worth mentioning, is that when it passes through that line, and if I get a spin up position, okay, again taking that spin up, if I put it again in a Stern-Gerlach experiment, again it will go a spin up and a spin down. In this way, things will go and the negatives will be one-sided and the positive signs will be one-sided. That means this spin up which has gone right on the top, again if you pass it to the Stern-Gerlach experiment, it will again result to another, again result to another. So repeatedly what it shows that it is quantized and it is very discrete. It shows what actually it is. Now, its personnel has put that it is a non-homogeneous or inhomogeneous magnetic field. The Stern-Gerlach experiment first actually gave us a very clear proof. Just a second. The Stern-Gerlach experiment actually proved that its first experiment to reveal the existence of spin, demonstrating the particles like electrons have intrinsic angular momentum. Also, you see what I have written in red, that the spin splitting into, just hold on. The splitting into two beams, why it has taken a silver atom? Because their orbital angular momentum was 0, right? Because it is in the s orbital. So you see how intelligently they have done. It has taken a silver atom and it has actually taken the electron. Why? Because the orbital angular momentum is not there. And the splitting it into two beams was due to the intrinsic spin. This is important. Why it got split up into two? Because it has got an intrinsic spin, and which can possibly take two values due to the magnetic field, which is either the up or the down. So the Stern-Gerlach experiment truly gave us, number one, that electrons have a spin. This spin is something which is very internal, and depending upon the magnetic orientation and the type of atoms that we are using, it will be discrete, it will be quantized, either having a spin up or a spin down. I will show it later in a video that if those particles which have got a spin up again is going through the Stern-Gerlach instrument, it will also show that it is again splitting up into two. Now you see this. So I have taken two parts, the physical space, that means the general space, right? It takes two turns. And it is the physical space, the up and down, it is separated by 180 degrees, right? And if I take a state space means the abstract space where the electrons are residing, they are 90 degrees apart. So that means 90 plus 90 plus 90, it will take 390 degrees in order to get back to its original state, where it in the physical state space, it is totally different. So I know that I am not making a real justice to spinors, that are a wild spinor, then there is a polyspinor, polymatrices. All these things needs to be explained. But as you understand, in the live sessions, it is not possible. I mean to say, it is not possible, but somehow I have not made it. But this will give you a hangover or what is a spinor, why spinors are important. The electron spin is one half. The most of the matter particles made of fermions are one half. That means it will change the sign if you use the general vectors, because 180 degrees sign will not give them back to the original position, and mentioning them will be faulty. So we need something which is called a spinor. Okay. Now we come to what is the Dirac equation. We made the necessary preparations. Now you see that what is the Dirac equation. Now the Dirac equation are actually, I have written all these 1, 2, 3, 4, and the last one is the Feynman notation of, but these are all actually Dirac equation, right? Different forms. So what it tells, number one, is that it is a relativistic equation. We all know that. It merges together special relativity and quantum mechanics. It describes fermions, most importantly, which the Klein Gordon equation cannot, because they are not taking into account fermions. Most importantly, it describes spin half particles. That means the entire fermion family. No, it is not as the spin and the revolve. I will tell you, I understand your doubt. It is personal. It is not a revolution, actually, it happens. It is something which is a property which is called chirality and parity transformation. It's very technical. Actually, these things cannot be told. You need a pen and a paper and a whiteboard to write things. It is because of the chirality that where the electron actually bends. If the chirality is towards the left, then it actually goes well with the weak force. If it's towards the right, this is something different. As I told you, electron spin, let me give me some time. I will make a session, YouTube session, I mean to say live session, where I will only speak on electron spin. And it is the foundation. I hope you understand, it's personal. So, and it explains also the fine structure of hydrogen. I'm not going to that. These are the implications. Okay. Now what we will do is that we will take part by part each of the part of Dirac equation easily and try to explain what those actually mean. And first I will talk about the I part, I, the imaginary part, imaginary number. Now, first of all, you see that I allows the wave function to include what is called an oscillatory behavior, obviously, because it oscillates, and that is the nature of the quantum particles. Second thing is that observables, which are like position, momentum, etc., which are represented by Hermitian operators, the Dirac equation, being a cornerstone of quantum mechanics, incorporates naturally, and it maintains a consistency. These are all happening because we are including the first element, which is I. And obviously, I is because of quantum mechanics, wave functions are generally complex valued function. I will show you later that when we talk about the gamma matrices, why this I has been included by Paul Dirac. Actually, to be very honest, you can tell that Dirac equation is equal to the square root of Klein Gordon equation. Dirac equation is equal to the square root of Klein Gordon equation. Now, if you see the derivation of Klein Gordon equation, there are certain square roots. Some of the square roots are used by this I, and some of the square roots Paul Dirac used gamma matrices. So that is why it is not, I mean to say, it requires a derivation, but it actually comes from here. Also, you will see that this I, the Dirac equation, unifies space and time into a four-dimensional space-time, right? So say, for example, if del, this one is equals to del by del I, that means del 0, the time component, and del I is the 1, 2, 3, 4, all the space component, then what it happens is that it must be treated totally differently, because in the Minkowski space metric, it has got a different sign. And this comes from the relativistic momentum equation, E square equal to pc square, which is the Einstein equation. So if I take I partial of sub 0, this is the last one on the right hand side, you see that it corresponds to the energy operator, and it ensures that energy is treated consistently in terms with the momentum operator. We use imaginary numbers. like dimensionless numbers who does relate to the Navier-Stokes equation, because my mathematics try to compute. Yeah, it is practically not possible. That's true. Yeah. I am vengeance. You're right. Why is that strange name? I am vengeance. Okay. So from here, what we can understand is that I is necessary in order to maintain that consistency, because time and space has to be dealt with. Another very important thing about I is that you see the Schrodinger equation also carries an I. Now, hear me out very clearly. The Dirac equation also carries an I. Now, the thing is that Schrodinger equation is a non-relativistic equation, but Dirac equation is a relativistic equation, isn't it? But under certain circumstances, if I consider that the particles are not speeding at the speed of light, that means Dirac equation can go back to what? Schrodinger equation. As we tell in case of general theory of relativity also, that under slow bodies which are moving, Einstein's field equations can go back to Newton's F equals to ma. Or the geodesic equation, which actually shows the movement of the body along a space-time manifold, can go back to what is called F equals to ma, with the motion of the bodies. So the I part is very important, because under slow moving bodies, it has to go back to Schrodinger equation. Otherwise, how can you make a equation in physics consistent? So since the Schrodinger equation includes I in the time evolution term, the Dirac equation have to include I in order to maintain the relativistic and the non-relativistic balance. In order to make the relativistic and non-relativistic balance. Oh, because you're a Batman. Okay, thank you. So from here, what we can see is that I is used because it accommodates the complex nature of wave functions, and this, it maintains the consistency with the relativistic Schrodinger and the non-relativistic one. Okay. Now we come to the second thing, which is a little bit complex, and I cannot assure that I can make you understand absolutely everything, but this again requires a little bit mathematical derivation, which is not present over here, and it is called the gamma matrices. Now, overall, what is a matrix that you understand? Gamma matrices are basically general 4x4 matrices. General, it is a 4x4 matrices. But one thing which I have not mentioned over here is that gamma matrices are follows what is called the anti-commutation rule, and it follows what is called a Clifford algebra. Now, Clifford algebra again is a separate subject, but just try to understand that it actually follows something which is on a very special basis, which is called a Clifford algebra. So, concerning this, what we can see that the gamma matrices are actually that I called it. These are the this is how the gamma matrix looks like. Now, this is something very important. You see one thing, that the gamma matrices indices 0, 1, 2, and 3, they are written on the top, on the indices on the top, right? And if I can take all those 0, 1, 2, and 3, then I can very well write it in an index called gamma mu. This is just similar to the Ricci curvature tensor Einstein field equations, those who are following my channel. Then it is gamma mu, right? And these are all contravariant gamma matrices. In tensors, we tell what? Contravariant tensor. If it is written on the top, if it is written on the bottom, it is a covariant tensor. Which country and what kind of masters that you're doing, it's personal, it depends on that. But gamma matrices is generally taken into account in the master's degree. Yeah, that's how it is. So now the thing is that all these 0, 1, 2, and 3, this actually representing space-time diagram. I mean, it's just a space-time, because space-time, oh, you're in India, right? So I think that it will be in the first year of MSc. You can check it, because I'm not very, nowadays I don't look into curriculums because I teach. So it is got a straight curriculum and we are teaching on that, right? So now the thing is that you see that gamma matrices have got what is called a covariant tensor. Sorry, the covariant indices, and it is not contra. It is not written at the low. But there is a question that why it is not written at the low. That means we are not taking the contravariant part. We are taking the contravariant part. We're not taking the covariant. Why? Because there is a relativistic invariance. I will show you what actually it is. It's very simple. Now, in the case of a special theory of relativity, we know that the four vectors, that is the four position, four momentum, okay, a four vector, all this actually makes a contravariant transformation. They undergo a contravariant. I hope you all understand what is contravariant. It's going in this direction, it's going in that direction, right? So if it is making a contravariant transformation under Lorentz transformation, then if the space-time is moving in the contravariant way, then then the Dirac index has to be done in a contravariant way. Otherwise, how will it meet up with the space-time mathematics? So here you see I h bar, which is a Planck's constant, which is followed by a gamma mu and then by a del mu. This gamma mu is a contravariant, but del mu is a covariant because the indices are right at the below. So what does that mean? It means a profound thing. It means that the Dirac equation involves the four gradient, which will come to that later. What is four gradient? Which is a covariant. And to construct a scalar, we need a scalar component. Why we need a scalar? Because if it is a vector, then it will create a problem. A scalar will just be Lorentz invariant. Are you getting my point? If you get a vector quantity in here, then again it will undergo Lorentz transformation. All those things will go. But if you get a scalar, then that scalar won't change. And we are done with the Lorentz invariant part. So here you see right at the bottom, gamma mu is covariant, contravariant, right? Del mu is covariant. And when we do this summation using Einstein summation notation, what we get is a scalar. And that is the best target, because if you get a scalar, that means the scalar won't change. And that is what it makes a Lorentz covariant. So here is a quick summary that the overall Dirac equation is a Lorentz covariant in nature. Remember, contravariant vectors transform in a way that preserves. That means it will preserve the Lorentz transformation. And by using gamma matrices, we ensure that the Dirac equation maintains its form. So this gamma mu is basically the space-time matrix, right? Which is contravariant, because in special relativity, space-time or the four momentum, they transform under contravariant. So contravariant to contravariant, things are easy. And gamma matrices must transform in a specific way under Lorentz transformation. Now, here is a note I will like to tell you. Those who are aware about tensors, I think some of you might know tensors. Gamma matrices are not strictly tensors. Don't make this mistake. Gamma matrices are different. They are anti-commutative. They follow the Clifford algebra. But it is something like tensors, we can say. But don't tell it that, oh, it is a tensor. No, it is not a tensor. So now you see this simple example that all these four vectors, they transform in a contravariant way. Gamma matrices also transform in a contravariant way. In a Cartesian coordinate, if we take x0, x1, x2, x3, right? And then we do a kind of a, contravariant transformation, then it will be del 0, del by del x0, del x1, del x2, and so on. But if we take a change of the coordinate, this change of the coordinate is as per special relativity, right? X prime 0, x prime 1, then you see that the tensors transform in a different way. X prime mu equals to del x prime mu by del x nu and then x nu. So it's a combination of co and contra and co and contra, which is actually creating a scalar, right? So from here what we get is this one. This means that Lorentz transformation in the opposite way. And in Dirac equation, the gamma matrices are used to couple the spinor field in the space-time. This is too technical. Their role is to maintain the equation's covariance. So from here, what we can understand is this one. Let me go back quickly to the next part. This is something which is, so it is covariant in nature. Gamma matrices is covariant in nature. In special relativity, things transform in covariant manner. So it gives us a kind of a well-maintained equation. So here you see, we can tell that gamma matrices are not tensors. As I told you, do not think that it is a tensor. It behaves or analogous to tensors. You can say it is a matrix valued vector in Minkowski space-time. And at the last, this is very important, gamma mu followed by del mu. So it is a contra versus co, which gives a scalar. That means it is Lorentz invariant. Right? I know it is going to be a little bit heavy, but just bear with me. I will make things much clearer. Now you see, just beside gamma mu, there is a del mu. And this is actually representing the partial derivatives of space-time coordinate. Very simple. This del mu is x0, which is time, x1, x2, x3. These are the 3 dimensions of space. Right? And this del mu describes the wave function psi. Now hold on. This psi is not a wave function. It is actually a spinor. But let us assume for the time being it is a wave function. Now remember, because the wave function is transferring in terms of both space and time, I will show you what it is. Okay. So gamma mu is basically paired with 4 gradient. And gamma mu is a contravariant, and this is covariant. It feels a lot to understand in just 1 year. Yeah, you don't understand in 1 year. Take your time, right? So to correctly contract it with ensuring that the resulting expression transform. Okay, let me show you this one. This is a much clearer and easier picture. So space and time in Newtonian mechanics was different, number one. Space and time in what you called special relativity is one manifold, right? So instead of a gradient, we have a 4 gradient because it tells both space and time are changing. Both space and time are changing, right? So because both space and time is changing, what do we need? We need partial derivative. And this partial derivative is this one, gamma del mu, which actually talks of the x, y, z, and t. Now, you might be confused that this is also, I am telling as a space-time derivative. This is also in space-time derivative. I will clear it up later. This is a different kind of a space-time equation, which is acting on a spinor field, right? And this is actually the physical space-time, which is taking into account, which is actually changing with the space-time coordinates. So the 4 gradient ensures, I mean to say this one, del mu, that the Dirac equation is again Lorentz invariant, and this invariance is crucial for any relativistic equation as it ensures consistency with special relativity. Okay, I know it won't be clear in one part. You need to take care again. And the last thing that we get is the psi part. And this is not a wave function, all my dear students or those who are hearing. This is a spinor. Right? And I told you what is a spinor earlier. That is why I made you understand first about the spinor and later about this part. So the 4 component spinor, I will show you what it is. It is a complex value function. Now you see what is this. Psi 1, psi 2, psi 3, psi 4. This psi 3, psi 4 can also be written with a dot, which is not a convention over here. So the first 2 spinor components, this states spin up and spin down with a positive energy. Remember, we told that Dirac equation actually tells what is, what is called an antimatter or a negative energy. Dirac at the beginning thought that this is a wrong. He must done something wrong with the equation, but later found that no. I think I don't remember the name, the person who actually discovered antimatter. The next 2 components, psi 3 and psi 4, they are also spin up and spin down, but they denote what is called the negative energy. Okay. So from here, what we can tell is that this spinor, the physical representation is that if you square it, then it will actually show you the probability density, which we started with Schrodinger equation, right? That it gives you the probability where the electron would be. Now with spinor, what it gives, first of all, you see on the left-hand side, I've written that it transforms under a specific way under Lorentz transformation. Spinor transformation is actually by SO3 and SU2 matrices. I'm not going into that. Second, Dirac spinor is not a wild spinor or any other. It is a bispinor. Bispinor means it account both for particles and antiparticles. It is a bispinor. Third is that Dirac spinor incorporates into spin half, which was not done in Klein Gordon equation. Remember. So it incorporates spin half particles. That means all the matter is being covered in Dirac equation. The fourth part is that Dirac equation naturally predicts the existence of antiparticles, and the Dirac spinor incorporates the effects of special relativity where mass and spin were intervened. Right? This is how the spinor comes in. And last but not the least, is m and c. M is basically the rest mass of the particle, although Dirac will take into account the moving relativistic mass also. Uh, the c is the speed of light. So the mass term is essential because it gives the particle's inertial energy, and the speed of light, obviously it is a relativistic equation, so it has to take into account the speed of light. So that's all for today's basic idea about Dirac equation. I hope that you got at least a hangover, isn't it? What it is. I know that there will be many questions about this, but I try to give you a hangover of what the Dirac equation is. That you understand it is too mathematical. It won't be possible that you can make it in one. So if you have any question in another 2-3 minutes time, you can ask me. Otherwise, we can wrap it up. How was the session? Can you give any feedback on the chat box? How was the session? Okay, it was a good session. Okay, I hope you don't have any questions as if itself. Very informative. Okay, thank you very much. Thank you, Ed. So I am getting a little bit late because extremely informative, loved it. Okay, please do share this live. Okay, so the question is, sir, is what if you can make content about Clifford algebra, spinor? Also, can you mention some books on regarding this? Yeah, I will do that. I mean to say, you contact me in WhatsApp, or you can email me. You all know my email ID. I will send you, if possible, even I can send you the name of the books. One book I was reading, I don't have this one, which is called The Strangest Man, and I just cannot stop reading that. I went to sleep yesterday at 3 o'clock night, period to that also 4 o'clock. But before even dozing off, I read few lines. It is about the life of Paul Dirac. It's amazing. The Stranger's Life. It is something. Got the Amazon link. You should read that book. I think we all love Paul Dirac, isn't it? Stranger. Graham Farmello. Yeah. Strangest Man. I can give this link also. Yeah. Check it out. Oh, how many links does not? No. This is the strangest. Yeah. After spinors, will you consider doing Lagrangian for Dirac and then going to Catherine coupling of two fields? Yeah. Actually, to be very honest with you, right now I would consider first the Dirac equation (ED) and make it more relevant, because I have not covered bispinors, Weil spinors, water spinors. This is not clear. So in the upcoming videos, I will make maybe one long video divided into 2-3. I will first make it to the Dirac equation more importantly. Well, the first video was just an overview. And yes, I'm going to consider the Lagrangian, but I'm not very sure that I would go into the Catherine coupling of two fields. I need to check it up. So yes, Dirac equation is going to take up few more videos, and we will do that. And yes, for Ankur, you can get in touch with me. I will consider the Clifford algebra, spinor algebra, etc. Spinor actually will take some time. It is going to take some time. It's not that easy to visualize. Oh, yeah. Okay. It's just an announcement tomorrow. I am lucky. Okay. I'm lucky to get Professor Joseph Conlon starting 8 p.m. Indian Standard Time. And he will be speaking on what I would say string theory. And not only this, he's a very knowledgeable person. So you can ask all your doubts related to general relativity, quantum mechanics. It covers string theory. It covers everything, isn't it? It covers every single thing. So you can ask your question related to becoming a theoretical physicist, asking questions about general relativity, quantum mechanics, standard model, particle physics, whatnot. I am also looking forward very strongly for tomorrow's podcast. So that's it. Thank you. Goodbye. Take care and stay safe and stay happy and keep on learning. Please do subscribe. And I all want, if you can just put on one-liner comment in the live session. That really helps YouTube to boost things and me also to give a lot of motivation. So I am not done with the Dirac equation. This is just a starting point. I just thought to tell you over the live, because in live we can talk a lot rather than videos. So I thought that I know this much. So why don't I teach you all? I have many questions related to gravity and standard model as well. So I am Vengeance, you're a Batman. So Batman is always a silent guardian. So be there tomorrow and you can ask your question. But please frame the questions properly, because he's from Oxford, he's an English person, so he would want something very precise, correct, and not going that, okay, this and that, right? These type of people are very serious, and yeah, so that's just to get through. I'm also trying to get in another person from theoretical cosmology. I don't know when will he give time. So anyway, thank you. Great going, and I hope you enjoyed it. Please do comment a little bit on the comment section of this today's live, and I will continue more with the Dirac equation. It's just the starting point. Take care. Goodbye.